Welcome to Woods Hole Research Center's 2020 KNEB webinar series. Thank you so much to the KNEB family for supporting our efforts to share our work with a broad audience. Woods Hole Research Center, for those of you who may not be familiar, is a relatively small organization of top scientists working with a global network of partners and stakeholders to not only understand but also combat climate change. And you're going to see that partnership and also that combination of basic science and solutions oriented thinking on display today in our discussion of the risk of northern fires, fires in the Arctic and boreal forests of North America and Siberia. Before we jump into that, I would love to get to know those of you who are joining us today just a little bit. We started this webinar series back in March, shortly after we and most of the rest of the United States had gone to a remote work scenario. We had to cancel our events, and this felt like a great way to stay in touch and be able to reach perhaps an even broader audience. And certainly we have found that there are advantages to the webinar format. For that matter, we are not constrained by geography. We can both bring together panelists and speakers from around the world and reach audiences around the world, and that's great. But there are also definitely some drawbacks to the webinar format. We wish we could see all of your faces, and for that matter, you know, it's great when you get to an in-person event to kind of look around and see who's in the room. And since we can't actually do that in the webinar setting, what we like to do is a few polls to try to get to know each other a little bit better instead. So I'm going to go ahead and launch our first poll here. And just let us know where you're joining from or where you live, and you can answer this question either way you like if you're joining us today from someplace that is not where you live. And I will tell you, it's been really fun to look at these results over the weeks and see all of the different places around the world where people have joined our webinars from. Today, we seem to have an audience that's even more than usual, heavy on US Northeast and Canada so far, as the votes are coming in, about 77% of you joining from the US Northeast and Canada, with the US West, I think, coming in a distant second place there, but folks from all around the US, from Europe, and a couple checking that other box. And if you've checked the other box and feel compelled to share where you're joining from, go ahead and jump into the chat and let us know where it is that you're joining from. Let's see, we've got about 77% of folks who have voted. We'll give this just one more second. I'm seeing one person joining from Alaska. Put that in the chat. So let's see here. The votes have slowed down. So I'll go ahead and end the poll and share the results. And you can see most of you from right here in our backyard, as it were, in the US Northeast and Canada, but definitely an audience from around the world. And that's great to see. And I have to say, it's really fun to also scroll through the list of all the attendees and see both familiar names and new names. So if you do me one more favor, and I'm going to go ahead and stop my screen share here. If you would do me one more favor and raise your hand if this is the first KNEB webinar that you have joined, the first Woods Hole Research Center webinar that you have joined. And this number has been dwindling over the spring and summer as our series has progressed, but this is terrific to see still a dozen or so of you, and the number still going up here, saying that this is your first time joining a Woods Hole Research Center event or webinar. So welcome, a special welcome to you for joining us for the first time today. Now, as I mentioned, today we're going to be hearing about the growing threat of fires in northern forests. Our last webinar a couple of weeks ago focused on the risk of fire in the Amazon, and one of the messages that really got driven home in that webinar is the fact that fire is not a natural part of Amazon ecosystems, that those fires are almost entirely human-caused fires. But then we often hear with, say, the US West, with California, that fire is a natural part of those ecosystems. So I'm curious, and I'm going to launch another poll here quickly. If I can jump to our second poll. Which one are the northern forests we're going to be talking about today? Are those ecosystems where fire is a natural part of the ecosystem, or is this an ecosystem where fire is an introduced phenomenon? And this is not about proving who knows more or less. This is just a little fun get to know you, and also so our panelists have a sense of where we're starting from. So a little over half of you, about 2/3 have voted now, and overwhelmingly the majority saying true, fire is a natural part of northern forest ecosystems. I'm going to go ahead and end that poll and share the results. You can see an 80-20 split there, true. Brendan, I saw you nodding your head. I guess that's 80% got it right? That fire is a natural part of northern ecosystems, but that situation is changing. So without further ado, I'm going to go ahead and introduce our main speaker, who is Brendan Rogers. He's an associate scientist in the Arctic program at Woods Hole Research Center. And Brendan is going to tell us a bit about his work and the Arctic program's work and what we're learning about the changing risk of fire in northern forests. And then after his presentation, he will be joined by a couple of panelists, the director of our Arctic program, Sue Natali, and also Peter Frumhoff, who is the chief climate scientist and director of science and policy for the Union of Concerned Scientists, to broaden out the discussion about fire in northern forests and also really dig into what we might be able to do about them. So Brendan, without further ado, go ahead and take it away.
Great. Well, thank you everyone for joining. So yeah, as Heather said, I'm going to take you a bit north from where we were a couple weeks ago looking at fires in the Amazon and talk about fires in our northern boreal forest, but really across the Arctic boreal zone. So these areas are dark and cold and wet much of the year, but during the summer months, they can get quite hot, they can dry out. And when you combine that with lightning and in the southern boreal, human ignitions, fires are a prevalent, powerful, and destructive force. So for the 80% that said true, that's true, corroborated. And the destructive nature of it exemplified by this photo. This was recently taken outside Novosibirsk in Siberia. Oops. So where do these fires occur? If we look at down in the North Pole, across the northern circumpolar zone, we can see some major burning centers. So what I'm showing here is cumulative percent burned over the 20-year period from 1997 to 2016. And generally we see fires in interior Alaska, central and parts of eastern Canada, a lot of the Russian Far East and sort of central taiga in Siberia, and in southern Siberia on the border between Russia and China. Typically, fires are not very frequent in tundra environments. Now, under a relatively stable climate, this is not a problem, as the fires are also stable over a long term and roughly balanced by ecosystem regrowth. But of course, we all know we're not in a stable climate. You've probably seen maps somewhat like this. This one is from NASA, and it's showing the temperature difference from the 5-year period 2015 to 2019 compared to the mid-20th century. And what probably jumps out are those big red splotches in high northern latitudes. That's a pretty distinctive feature of the climate system. It's a well-known phenomenon. It's called polar amplification. And essentially what it means is that the high latitudes are warming twice, if not faster, twice as fast as the rest of the planet. And along with those temperature increases, we're seeing an intensification of the natural fire regime. So here I'm showing a graph across Canada and Alaska. We have much better data there. I would say that we're also working on getting better long-term data for Siberia. And this graph is part of a partnership, or part of the result of a partnership between WHRC and the Union of Concerned Scientists, including Peter Frumhoff, who's a panelist, and Carly Phillips, who's a fellow and a joint postdoc between the two institutions. And so we have pretty decent data across Canada and Alaska. And if you look at the trends in burned area in the boreal and Arctic zone, it's distinctively increasing on average. And the reasons for this are relatively simple in that we're dealing with longer fire seasons. We're dealing often with more extreme fire weather. And as a double whammy from climate change, we're actually dealing with increased lightning. As the atmosphere warms, it can hold more energy, and there's more convective energy, and that leads to more lightning ignitions. So we're seeing intensification of the fire regime across Alaska and Canada, and we certainly suspect it across Siberia as well. We're also seeing some new types of phenomena, or at least that we sort of are discovering new phenomena that we haven't seen much before in the past. One of those are these these fires, they're called overwintering or holdover fires. And the media has really grabbed onto this the last few weeks and called them zombie fires because they essentially refuse to die. And so what the phenomenon is after a flaming front comes through a previous summer, the fire can actually continue to smolder in the peat and the soil organic layers. Sometimes it's fueled by methane deposits and it's insulated by snow in the wintertime. And then after that snow melts and temperatures warm up and the soil dries out, that fire can reignite. And here's just a nice visual from satellites. It's a satellite false color image. But what I'm showing here on the top left panel, that's a fire from the large fire year of 2015 in interior Alaska. That white outline shows the fire scar. Then in the top right panel, it's a look at the region before snowmelt in April the following year, 2016. The bottom left panel then shows at the end of May in 2016, you can see a bunch of new fires flare up at the southwestern portion of that old fire scar, leading to a new fire scar there in panel D. And so we've seen reports of this on the ground in both Alaska and Canada, and certainly some evidence that that's happening in Siberia this year. And what we do know is that these fires are more common after large fire years, which we're seeing increasingly across the Arctic. And I would say in total, all of this phenomena is really tied to climate change. So what's happening this year? Well, the big story this year is Siberia. So this is another temperature anomaly map. It's showing the anomalies between the first 6 months of 2020, January to June, compared to 1951 to 1980 average. And the big red splotch that jumps out is Siberia, Eurasia in general, but northern Siberia in particular. So it was a really warm and dry winter in Siberia. Snow on average melted about a month early. Across the 6-month period, the average temperatures are about 5 to 6 degrees Celsius warmer than average. That's 10 degrees Fahrenheit, but it was certainly much hotter than that in given weeks and days. It was the hottest winter in Siberia in its 130-year record. To note, the previous, or the second hottest, was 2019. And in many of the villages and cities, the northernmost villages and cities on our planet, we're seeing temperatures over 90 and 100 degrees Fahrenheit, so sort of shattering all kinds of heat records. In tandem with this heat, Arctic sea ice has been declining. It's actually at its lowest recorded levels ever for this time of year right now. And a study just came out last week showing that the magnitude of this heat wave is virtually impossible without climate change. So what have the impacts been on the residents? Well, there's, I guess there are some positive ones and potentially more recreation opportunities like swimming, but there's also a lot of negative ones. There's been reports of more mosquitoes, documented health problems, lower fishing volumes, and of course fires. So the fires are not just restricted to the forest, they're burning more and more of the tundra, even though historically the tundra doesn't burn that frequently. This is a satellite image of fires burning north of the Arctic Circle in Siberia a few weeks ago. 2019 was the largest fire year in Russia in about 20 years. And this year so far seems worse than that. There are also implications, or I guess interactions with COVID and coronavirus, in that there's evidence to suggest that with people on quarantine and lockdown, they've been spending more time in the forest and igniting more fires, and fire suppression activities have been negatively affected by COVID. So there might be more fires now than there would have been otherwise. Everything's kind of connected. And here's just a photo of one of those fires near the northern city of Cherski, where Natali, who's a panelist, has spent many years doing research, as well as Max Holmes and others at the research center. So one diagnostic I want to look at is fires north of the Arctic Circle. So this is pretty far north, pretty much tundra, and again, the region that fires are historically not that frequent. So this is one such graph of what's happening recently. This is put out by the Copernicus Atmosphere Monitoring Service, looking at wildfire carbon emissions during the month of June north of the Arctic Circle. And you can see last year in 2019, it was far above the previous 15-year record, and this year is above that. And here's another way of looking at it. This was a graph put together by my colleague Sander Veravabek in Amsterdam, and it's looking at active fire pixels. So essentially when a satellite travels over an area, if it's hot enough from a fire to trip trip an algorithm in the satellite, it gets painted as an active fire pixel. This is number of those pixels over the course of the year from 2001 to current. And you can see all those gray lines in the bottom right are 2001 to 2018. 2019 was far above that. And as of last week, when this graph was updated, it's right now we're above last year. But I do want to note that the problem is certainly not restricted to the high north above the Arctic Circle. In fact, most of the fires are occurring in the sort of central and southern boreal, where there are additional problems, both because trees are sort of in certain places at the edge of their environmental tolerances in terms of what they can withstand, but also because of direct human actions such as logging. So this is a photo taken in Siberia. And because logging opens up access to other people, because it generally results in a drier and warmer microclimate, and in this case, slash is not really dealt with, there are a large number of fires around cut blocks. So it's both climate change and as well as our mismanagement. So where are we going to in the future? So I want to go back to this graph that Carly Phillips made and look at burned area over the last 60 years in Canada and Alaska. Again, we're working on this in Siberia. We hope to have a better idea pretty soon. But where are we going? So we looked at all the available projections of what might happen to fire, to burned area, to mid-century, which is a policy relevant time frame, across Canada and Alaska, and it generally results in a picture that looks like this. As you might expect, with increased warming, we expect more fires and potentially an amplification of that trend. So I asked, why should we care? Why should we care? Those in lower latitudes, the population density is not that high in the Arctic. Why do we care about all these fires? Well, I think there's a lot of reasons we should care. I'll try to name some of them here without going into too much depth. On the right, you can see this is going to be a sort of replaying movie of fires last July, mainly from Siberia and Alaska, but also Canada. And you can see the smoke being transported across the Arctic. So this smoke contains a number of compounds. One of them is called black carbon, and black carbon, when it's deposited on snow and ice, is a major warming factor. In fact, it's the second or third largest climate forcing after CO2 and probably methane globally. In the Arctic, black carbon comes from two main sources, both from fossil fuel transport from lower latitudes, as well as Arctic boreal fires. And in large fire years, fires can be roughly half of that effect. But the smoke also contains a number of nasty chemicals that we breathe, particulate matter, PM2.5, other species that can get into our lungs, actually get into the bloodstream. In regions with large fires, the air quality often exceeds the EPA's highest danger rating. And from an economic perspective, I think the impacts are hard to measure, but it's certainly in the billions of dollars, probably hundreds, if not more, billions of dollars per year globally. I would say also that small villages in the Arctic are disproportionately affected. They just don't have the resources. They don't have the access to things like clean rooms and smoke respite centers. Smoke also impacts aviation. This is a major way that people of the Arctic get around in the summer months. And if there's too much smoke, you just can't fly. Similar impacts on tourism and recreation, which can essentially be brought to a halt. Natural resources like subsistence resources, direct impacts on infrastructure, and really a whole host of other impacts that I'm not going to go through here, but just to say that these fires affect society in a number of ways. Now, you might guess one of the ways that we sort of care a lot about from a climate perspective is the carbon story. So when fires come through these systems, these boreal forests and the tundra, they emit a lot of carbon. In terms of carbon emissions from fires per unit burned area, these are some of the highest levels globally, effectively on par. The only thing that might be more are peatland fires in tropical areas like Indonesia and deforestation fires in the Amazon. But otherwise, these fires are pumping out more carbon per unit area than most other fires globally. And it's not because the trees are big. The trees are actually usually quite small. As you can see from this photo, most of the carbon being emitted is coming from the soil, these thick duff layers that often accumulate in these forests that have a high carbon content and take years and many decades really to regrade. And the situation is made worse in areas that are underlain by permafrost because that soil, those organic layers that are on top of the permafrost, insulate it from warmer temperatures in the summer. And so when you have fire that burns off those layers, you can get permafrost thaw, you can get rapid permafrost degradation, which adds to the emissions. So just a couple sobering numbers about the carbon side. You know, globally, boreal forests are about 1/3 of all forests in terms of aerial coverage. But our best guess is that they store about 2/3 of global forest carbon. Again, we're not talking about the trees here. They're part of the story, but a small part. It's what's in the soil. And if you combine what's in the boreal forest with the tundra, permafrost contains about twice as much carbon as in our atmosphere, both what was there before the Industrial Revolution and everything we've done in terms of our society during and after the revolution. So there's a lot at risk. So if we then turn to that graph that was showing burned area projections for the next 30 years and then turn it into carbon, we get a picture that looks somewhat like this. So now the units being shown are gigatons of CO2 per year. And I should note that some of this carbon will certainly be resequestered by regrowing forest and tundra, but our calculations show that really won't have much of an effect on the atmosphere in terms of radiative forcing and warming by mid-century. And a couple numbers to put this in perspective. So if you look at a state like California. California, if it were its own country, would be something like the 5th largest economy in the world. The annual emissions coming from California are about 0.36 gigatons CO2 per year. So we're sort of in that range, heading toward that number pretty soon in terms of an annual average. Another important perspective to have on these numbers is that, you know, if these projections are true, this represents between about 2 and 5% of the allowable emissions we have to stay under 1.5 degrees Celsius increase from pre-industrial temperatures, which is a policy relevant target. And also to note, this of course doesn't include Siberia. The other thing I would say is that this type of information is essentially being left out of the models, not out of negligence, it's just not in the models, and we need to do a better job of getting it into the models. But those models that are informing the scenarios of what we need to do to stay under these temperature targets, like 1.5 or 2 degrees Celsius. So this information is essentially not being accounted for. So what should our policy response be? And I have 3 main answers to that, or suggestions, I guess. The first one is both the most important and the easiest, and that is just we need to cut fossil fuel emissions. You know, the best time to reduce our fossil fuel emissions was probably about 40 years ago, and the second best time is right now. You know, from a scientific perspective, the more that we learn about the Earth's system, generally, I would say the worse it gets in terms of feedbacks to climate, and this is the #1 problem. But to aid that, like I mentioned, these emissions from fire and permafrost are effectively not in the models that are informing the scenarios of how we stay under these temperature targets. And so the second thing I think we need to do is integrate those emissions so that when we come up with things like nationally determined contributions, we have a clear picture and accurate numbers of how we actually stay under these temperature targets. And the third policy response I would say is really interesting and deserves more attention. And this has been the main focus of this partnership with Union of Concerned Scientists, is that if we're headed down a path that's consistent with something like 1.5 or 2 degrees Celsius, fire management, mostly fire suppression, but other types of management, may represent a real viable mitigation strategy. And, you know, I guess the point here is that we really no longer have the luxury of just reducing fossil fuels to stay within these important thresholds. We need help from all the sectors that we can get it from. And so we've done some work to suggest that boreal fire management might be one of those pieces, one of those sectors. So just a little indication of why we're thinking that. So we focused mainly on Alaska. That's where we have the best data. As I mentioned, most of the fires in Alaska are occurring in the interior. And the way that fire management is done is that the land is divided up into these zones called fire management zones. You can see there on the map on the left, ranging from critical, where essentially all fires are put out, to limited, where they're essentially monitored, and then a couple zones in between. And on the right, you can see the average fire size on a log scale for those different zones. And so there is a lot going on here, but we've done some modeling to strongly suggest that fire management is having an impact on fire size and hence burned area. And that should also be noted that really the main objective of fire management is not always to reduce fire size. It's usually to protect values at risk, but it's still having a notable effect. We've also integrated some economic data, and if you integrate that economic data into a model to look at how much it actually costs, given current fire management, to avert 1 ton of CO2 emissions from fires, it's about, on average, $11 per ton. And so that actually winds up being on par or potentially even cheaper than other emissions reduction strategies or negative emissions technologies. And here's just a few numbers to guide that range. So utility scale photovoltaic solar, onshore wind, afforestation or reforestation, direct air capture, and then here's where our best guess of where boreal fire management sits with a relatively large spread. But we also have reason to believe that we could potentially make this more effective with things like more funding and perhaps directed funding towards carbon, perhaps strategically placed operational centers, perhaps more permanent employees, and in an effort on initial attack and early detection. So I'll end it there. I think my main points to say on this matter are that fires are clearly increasing in northern forests and tundra because of climate warming. The problem is generally getting worse and is expected to continue. There are impacts on society at multiple levels, and the feedbacks to climate change are particularly worrisome. In terms of what we need to do, from my perspective, I think we need to continue sounding the alarm about fossil fuel emissions and sort of negative impacts on the Earth system and feedbacks that result. We need to get these emissions from fire and permafrost in global budgets, and we need to keep exploring other direct interventions such as fire management for near-term mitigation options. So with that, I'll end it and pass it back to Heather.
Great. Thank you so much, Brendan. And I'm going to invite our panelists at this point to start their video and turn on their microphones as well. And to let you all know how the rest of this webinar, the remaining 32 minutes that we have here, will go. I have a couple of questions each for Sue and for Peter, but we want to leave time for your questions as well. And I know a couple of questions have already popped up in the Q&A and in the chat, and I've seen a couple of people raising your hands. If you would please, our preference would be if you can put your questions into the Q&A. That's the main space that I'll be monitoring for your questions. So go ahead and type those questions into the Q&A, and we'll get to those in just a couple of minutes. But as I said, I do have a couple of questions for our panelists before we open this up completely. And I would like to start with you, Sue. Again, Sue Natali is the director of the Arctic program at Woods Hole Research Center. And Sue, a lot of your research focuses on permafrost and permafrost thaw. And Brendan already mentioned that this rather surprising statistic about the amount of carbon that these northern forests hold globally, and that a lot of that is actually in the soil. So can you tell us a little bit more about kind of the interaction between these fires, which we tend to think of, I think most of us, I certainly have always thought of forest fires as being a phenomenon that's about trees, but what's going on with the soil and how that ties in with this phenomenon of permafrost thawing and melting?
Sure, thanks, Heather. Is my volume okay?
Yes, it is.
Okay, yeah, so Brendan had mentioned this. When fires burn in northern regions, because there's so much carbon that's in the form of organic matter below ground, that the fires also don't just burn above ground, but they also burn the soil itself. The trees, the moss layer, the soil, they act as a really good insulator of the permafrost. So it gets very warm, as you saw this year's 100 degrees Fahrenheit in some places in Siberia. It gets really warm in many places of the Arctic in the summertime. And so this summertime insulation is really critical. And, I think about it like if you have a cooler, right? I mean, you burn off the top of this insulating organic layer. It's like opening your cooler on a really, really warm summer day. And you can imagine what's going to happen. The ice is going to melt. Your drinks are going to get really warm. And so the importance of this is that, you have this initial effect with the fire. And then, one of the other impacts when we're thinking about sort of energy transfer into the soil is you have this initial albedo effect that the ground is very dark. But that changes relatively quickly. This long-term impact on permafrost thaw can last decades, in some cases longer. It takes a really long time for that organic layer to build back up. So sort of placing this permafrost at increased risk of thawing. And sometimes that means that it's thawing gradually, but there's been other times that I've seen it where it's causing these, you have a combination of a fire and a really warm year, and you can have these abrupt events where the ground is just cracking and collapsing. And so this is, quantifying that is really tricky. It's not in the models. I mean, the fires aren't properly in the models. The permafrost isn't properly in the models. But I think it's like when we think about being cautious and thinking about taking action, this is, to me, one of the big reasons why acting now is really important, because we have this sort of multiplier effect of fire.
Peter Frumhoff, our other panelist, as I said, the chief climate scientist and director of director of science and policy at the Union of Concerned Scientists. Peter, can you just expand on what Sue was saying about the fact that the carbon released from these fires and from the melting, thawing of permafrost are not included in models? What does that mean in a sense, for the policies that are being created to address climate change?
Thanks, Heather. I'm happy to respond to that. Let me just say at the outset that what a pleasure it is not only to join this webinar, but also a privilege to collaborate with Brendan and colleagues at the Woods Hole Research Center. We at UCS, we're sister institutions with a real shared commitment and complementary strengths around making science actionable to inform policymaking around climate and other issues. And so this has been a wonderful partnership, as Brendan alluded to. So let's put this in a global carbon budget context, right? Every year we release roughly 40 billion metric tons of carbon dioxide to the atmosphere, mostly from the burning of fossil fuels, but also from land use change and fires as a part of that. And we've seen about a degree global average temperature increase, Celsius, so far. The Paris Agreement tells us that we need to stay within 1.5 degrees to stave off the worst impacts of climate change. And the best science tells us that we need to bring our carbon emissions net, no more carbon coming from the atmosphere, to zero by 2050, by mid-century. At current rates of emissions, we only have so much carbon budget left, right? And as you say, the carbon budgets that we've calculated don't include emissions from boreal fires. Just assuming that 40 billion metric tons, we have about 340 billion metric tons that we can release in a global carbon budget to stay below 2 degrees, 1.5 degrees. That's about 8 years of burning at the current levels. To bring that to zero requires a dramatic reduction in emissions to net zero, carbon uptake, as well as bringing fossil fuel emissions down. But because we haven't included, let's just say, the fire emissions from boreal forests, that's adding another, as Brendan highlighted, another roughly 5% of global emissions that we're going to have to contend with, that we're going to have to avoid those emissions in order to have a chance of staying within this 1.5 degree target. So it makes our challenge worse, right? It makes it harder because there are emissions that haven't been accounted for both in the models and in the policy. I think the good news, because it's important to highlight that there is good news, and this comes out of the research that Brendan was alluding to, is that it appears to be, at least in Alaska, really quite cost effective to be able to reduce those emissions, to bring them back to historic, ecologically sustainable levels. And by trying to design fire management budgets to have a carbon metric, in addition to protecting infrastructure and lives, there's a fighting chance, I think, that we can keep those emissions from exacerbating the problem. But we have to quantify them first in order to know what it is that we need to do. And that's the beauty, I think, of this research.
Yeah, as you're talking about our carbon budget and the added challenge that not accounting for these emissions presents, I'm thinking of, trying to balance your bank account, and if somebody's stealing an extra $20 from you every month, it's kind of hard to balance your budget, right? If you don't have everything accounted for, it's hard to figure out how you get to the right balance. So Brendan and Peter, I would love to hear from each of you a little bit more about this collaboration and the work going on between Woods Hole Research Center and the Union of Concerned Scientists, particularly on this policy front. We've got a number of people asking for more details on fire management and what that would actually look like, and also, for that matter, how we actually get these emissions accounted for. So what kind of work are you guys doing together to actually put this growing understanding of the problem into the policy realm?
Brendan, you want to start off?
Sure. Yeah. I mean, I would say, echoing Peter, I think it's been a really wonderful partnership, because what we're doing is, we're conducting science, but for the impact of influencing policy. And so, we've come at this question from a few different angles, from like a science modeling perspective, from an economic perspective, and all signs are pointing to a fire management as it's currently employed is effective. And I can give more details on sort of how fire management is done if that would be relevant. But it's effective at limiting fire size. Like I said, even though in a lot of cases, the purpose of what they're doing in terms of fire suppression is not necessarily to limit fire size, but it's to protect values at risk. So it's effective, but it's also cost effective from our economic analyses. So, we're at the stage now where we sort of believe in these results. We are currently publishing those results and hope to make a policy push. But I would say that what that looks like really depends on what happens this November. So Peter, I don't know if you want to speak to the policy implications a little bit more.
Yeah, I'd love to, because I think there are tremendous opportunities here, right? And I don't say that about all climate issues, but this is one that I feel quite optimistic that we can make a dent in. So currently, there's about $3 billion spent every year in fire management in the United States. 96% of that is focused on the lower 48, and not surprisingly so. Alaska gets relatively little attention from federal fire management dollars, and it's mostly, as Brendan highlighted, focused on infrastructure, on places where people live, which makes sense, except when you take account of the carbon consequences and the global climate consequences of not preventing or limiting fires in those other parts of Alaska, and by implication in Canada as well. Where if you imagined having carbon as a metric to inform investments in fire management, you might increase your fire management budgets in Alaska and perhaps in Canada in order to keep that carbon literally in the ground. And so we've put some numbers on it, and those numbers will matter for policymakers. And I have to say that to be very policy or maybe even political about it, you imagine a Senator Murkowski in Alaska who cares a lot about her constituents and may not come at this from a climate perspective, but will care about the smoke implications and the jobs implications and the public health implications and the tourism implications. And there may be lots of ways to reach decision makers. And so our intent as the paper gets published is to find ways to present, package, inform, translate our technical analyses into forms that connect with people from where they are, but in particular decision makers, both in Alaska, but importantly in Washington as well.
So Natali, this is an effort, not this specific project with Brendan and Peter, but more broadly, the effort to bring emissions from permafrost thaw to the attention of policymakers, get them incorporated into models and into globe and carbon budgets is also something you've been involved with. And I want to hear about that. I also, though, hearing Peter talk about the health concerns and the personal impacts of these fires. Brendan was mentioning the extreme heat that we're seeing this year. Obviously, because of COVID, you're not in the Arctic this summer as you normally would be, but you were last year. And again, there were incredibly high temperatures, fires. While doing your work, you encountered the smoke and the temperatures. Can you just give us a sense of what it's like on the ground in these kinds of conditions?
Sure. Yeah, so last year was another record year for the Arctic, and it was quite warm in Alaska last year. And so when I was there in the tundra, it was 90 degrees Fahrenheit. And that's, if you can go swimming and go into the ocean, that's wonderful. But if you're out there working, it's actually pretty challenging, particularly in the tundra when there's not any shade anywhere to be found. And it's also really smoky. I mean, it gets hard to breathe, even when the fire's not like right near you that you're feeling the heat, but just the air's quality gets really low. And then the other challenge of this is that we were working in an area that there had been a fire 5 years previous, which had burned the ground, which made it hard to walk on the ground because it had burned sort of the permafrost thaw combined with the loss of this ground structure because it was burned meant that you could walk at times and your leg would fall into the ground up to your knee or even higher at times. So it's really challenging. And, you know, I feel that, and I'm a scientist who was up there for a really short period of time. And so I think about people who are living in the Arctic who don't have air conditioning. And so they're not indoors with the AC on and like getting away from it. And so this is it's a serious problem, and it's a really serious health problem for people who are living in the Arctic. And there are many, I mean, yes, it is less crowded than it is in the lower 48, but there are many people in the Arctic, and there are many people who are experiencing the impact of this increasing fire frequency and severity.
So back to the previous thread, thank you for sharing that experience, but back to this kind of previous thread that we were talking about with how we get things, these carbon emissions actually accounted for and into the policy realm. And we've got a couple of questions along these lines. When we say, you know, we need to account for these emissions in models and in budgets, what does that actually entail? And Sue, that's something that you've been involved with for a while. So how do you go about doing that?
Yeah, so I'll say a few words and then I'll invite Brendan to fill in some details. There's a number of ways. I mean, one, you advance the science, and then at the same time, you're working with the policy community. And one of the things that I think is really important is that you're doing those hand in hand. So you're not doing your science and then putting it out there and hoping that it's useful for someone. So knowing the metric, the language, what it is that the policy community can ingest is really important at the start of a project, not at the end of the project. And so one of the things we've learned from working with partners is that this RCP 4.5, RCP 8.5, which people may have heard of, it doesn't always resonate. What we really need to know is what is the reduction in the carbon budget if you want to stay below 1.5 degrees Celsius? What is the reduction if you want to stay below 2 degrees Celsius? And so it's not that trivial to go from one to the next if you do your science in this framework of RCP. And so a project that Brendan and I are working on with others at Whistle Research Center is to incorporate fire, incorporate permafrost thaw, incorporate abrupt thaw into these models so that we can have a better sense of what do we need to do. And then taking that information to the policy community. In some ways, it's just providing the knowledge, right? I mean, how much is of your budget is being taken out every week, right? How much do you need to account for it? But then it's also increasing the urgency. Like, this is something that needs to be dealt with. And yes, there is uncertainty. There will always be uncertainty, but there's a lot of risks, right? So understanding what the range of possibilities is really important to be able to communicate that to the people who are making decisions.
And for those who are not, as you are, working in the research realm with RCPs on a daily basis, right? Those are essentially the different scenarios that climate models consider, the different emissions scenarios that are being considered. But to that point, right, it's about finding the right language to present this to people, not just the right language, but I love what you're saying about, you know, making sure from the beginning that you're framing your work and actually delivering the right kinds of numbers to actually help people. So Brendan and Peter, give us a little bit of a deeper dive into what you guys are doing in that realm. What is the information that people need, and how are you getting that to the people who need it?
Yeah, I'll maybe piggyback on Sue said and mention a few things. So I very much echo the comments that, you know, we need to be looking at scenarios that policymakers actually use. There is a bit of a disconnect between the types of scenarios that modelers use and the types of scenarios that policymakers are looking for. So that's one problem. The other problem in terms of why these emissions aren't accounted for is more of a scientific reason, but the models that get used, these big global models, when modelers are developing them, they're in terms of fire, for example, right? They're thinking about fires not necessarily in boreal and Arctic zones, and so they're thinking about the effects on trees. So most of these models, if they have fire, they're not burning the soil. And one of the things I tried to highlight is the fact that most of these emissions are coming from the soil. Because that happens, they certainly don't have the interactions with fire and permafrost, right? So these models are lacking sort of essential information. So one of the things we're hoping to do is do analysis, develop sort of different types of models, and then work with the global modeling community to get, to sort of develop the other models to get them to that place.
So
Because
if
those
I can
models.
interrupt you for 1 second, I mean, why isn't that information in there already, right? If you guys can sit here and say, this is the process that happens, that soil stores carbon and it burns and that emits carbon, why isn't that already in the models?
I think it just needs a focused effort, right? Like I've been involved over the years with the one of the main modeling communities in the U.S., out of NCAR, the National Center for Atmospheric Research, and they have like a good team of 10 or 12 people, but they have to be involved in these international assessments, and they have to interact with the community, and they have to develop the models, and they have so many things going on. They don't necessarily have a person that's looking at the boreal Arctic zone. So what we're trying to do is help them out, right? We're trying to say, okay, these are the important issues. This is how you can sort of put it into your models. The scenario question is really interesting too, because permafrost, you have to sort of do your models in different ways. And what I mean by that is, if you take something like a 1.5 degree Celsius target, the primary way that the IPCC and organizations like that look at the carbon budgets is, okay, how much carbon do we have to emit until we hit that level, that 1.5 degrees Celsius level? But that's not the end of the story. Often the warming is probably going to continue after that. And because permafrost and fire have these long-term sort of responses, right? They can keep emitting carbon. Permafrost can keep thawing. Fires can keep burning for tens, almost hundreds of years. What you really have to look at is get up to that 1.5 degrees Celsius and then come down. And most models aren't doing that, right? So that's another thing we're involved in. We're working with a type of model where we can do those types of scenarios to really inform policy in the right way. Because if we give them a number that's what do you have to emit right when you get to that point, that's not really the whole story, right? Because permafrost and fire will keep emitting after that and keep feeding back. I don't know, Peter, if you want to speak a little bit.
Well, I want to piggyback on this in a couple of ways. One is I just want to acknowledge something in the chat, if I may, from a colleague of ours, Werner Kurtz in Canada, who says, please emphasize you're talking about global models. The models we use in Canada for carbon reporting do estimate fire emissions, carbon dioxide, methane, N2O from biomass, and so on. You're correct that feedback from permafrost is not included. So just to put that out there, thank you, Werner. It's nice to hear from you and good to know that you're on. I wanted to note, though, that there are two gaps, right? One is about incorporating quantitatively emissions from the Arctic and from boreal fires in particular into climate models. The other is incorporating the notion that we can do something about them in the minds of a range of actors. I have to say that when we started this collaboration to just quantify what emissions might be coming from boreal fires in Alaska, to really put a number on it, the pushback we got, I certainly got, and I think Brendan, you did as well, was, well, that's all well and good, but those fires that are not near, no one's going to put them out, right? This is just not conceivable. They're too far away. They'll be way too expensive. It's not going to, it's not what we do. It would require a major change, major cultural change in the way in which fire management takes place, all of which might be true, but you don't really have an opportunity to have that conversation until you can bring both facts and a range of considerations, including impacts and benefits from that kind of suppression into the equation. So there's a gap both on the incorporation of emissions into the models, and there's also a gap on the incorporation of the notion that fire suppression, appropriately sustained and at appropriate levels, could be a cost-effective and meaningful part of the climate solution. That's a gap as well. And I think a significant part of our initiative in terms of doing outreach around this work will be to try to close that gap as well.
So while we're on the topic of suppression, we've gotten a number of questions about what that suppression actually involves. Are they toxic chemicals? Are there other effects that need to be taken into account when you consider a suppression policy? And for that matter, are there options that might be more on the end of fire prevention as opposed to suppression once they start?
Yeah, those are really, really good questions. So yeah, fire management broadly means a bunch of different things. It can be prevention, and that is certainly important. Part of the issue with these boreal and Arctic regions, they're extremely vast, right? They're very large. And so prevention in terms of what a main form of prevention is, for example, modifying what are called fuels, the vegetation. And so the like in Alaska and Canada, the conifer forest, the black spruce, white spruce, jack pine forests are very flammable. And so you can convert those to deciduous species like aspen and birch that are less flammable. And that is done around a lot of population centers, and it's effective. It's hard, it's difficult to imagine that being done over the millions of hectares of forests out there, because it also requires continual treatments that eventually forest succession will happen, and that will no longer be effective. So suppression winds up still being the main way that fires are managed. And I would not consider myself an expert on fire suppression. What I would say though is that what we identify in terms of the main lever, at least from my perspective, is what gets called initial attack. And so what that means is when a fire is detected, maybe someone's flying over, it gets reported by a citizen, or increasingly they're using near real-time satellite data. For example, in Alaska, they have the option of what to do. And that most of Alaska, like I showed, is in that limited zone, which essentially means don't monitor it. So last year, one of the most devastating fires in Alaska was called the Swan Lake Fire. And that started in the limited zone. And it was not initially attacked because it was unlimited, but it eventually grew and spread and wound up having a major impact on Anchorage. And so if, for example, the managers had more leeway, and if they had more resources to go after initial attack, one other fact I want to mention on that front, that when you look at a place like Alaska, the majority of fire ignitions are happening in June. The majority of area that actually winds up burning is in July. So there's often a long gap between when a fire starts and when it winds up burning the most area. And so if there was an increased effort on initial attack, especially for the carbon metric, I think it could be quite effective.
There are a few questions here going back to some of what you said, Brendan, about differences in trends that you are seeing both in warming and in fire between the North American Arctic and Siberia. What do we understand about what's driving those differences, and what does that mean, again, on a policy front, both in terms of the different tactics that might be needed and also opportunities for collaboration?
Yeah, it's a really fascinating question. I'm really interested in the sort of differences between the two boreal Arctic continents. So I think part of that question might be motivated by that map that I showed, which was the recent 5-year temperature anomaly compared to mid-20th century. I would say that's still a relatively short amount of time to be looking at trends. The climate system tends to have these sort of decade-ish long oscillations in terms of responses and trends. And so even because that map, for instance, didn't show Eastern Canada or Central and Eastern Canada as that warm, it might have even been low. I have to look. It doesn't mean it hasn't been warming since mid-century. It just means for those 5 years, it wasn't as much. So if you look at other maps looking at longer term trends, or like a 20-year or 30-year average, Alaska and Canada are warming essentially as much as Eurasia is. And a lot of it's due to that 5-year pattern. There are, though, I would say, some really interesting differences between the two continents. For instance, the vast majority, almost every fire that happens in the boreal forests of Alaska and Canada is a high intensity stand replacing, all the trees are killed fire. Whereas that happens in Siberia, but actually the most common type of fire is a surface fire where the trees are actually not killed. And there's some really interesting reasons for that. But it suggests that the responses of these different areas might be different, right? And you could take that a number of different ways. One path is that there's actually more potential for higher severity, more tree killing fires in Siberia, since that fraction of stand replacing fires could grow. On the other hand, there are other types of data and models showing that Siberia, in terms of photosynthesis, in terms of carbon uptake, might be sort of doing better than Alaska and Canada. And it might have to do with those stand replacing fires, as well as differences in tree species and differences in permafrost extent, differences in the climate dynamics. So I guess on the whole, there are some really interesting scientific questions there, but I would say, at a sort of meta basic level, it is warming very quickly in Alaska, in Canada, Fennoscandia, Greenland, Siberia, all the north. And the pattern of increasing fires is pretty prevalent.
Sue, are there similar differences or distinctions between what you're seeing in North American Arctic and Siberian Arctic when it comes to permafrost processes as well?
Yeah, I mean, there's a lot of trees on permafrost in Siberia. I mean, I think that's one of the things that most people aren't that aware of. And the thawed ground is quite shallow. So the trees that are growing there are growing, they can deal with this, which is one of the reasons potentially why they're, on permafrost. And so, even in some cases, I think where you don't get stand replacing fires in Siberia, you still have this sort of loss of the surface organic layer. You see areas where you have ground collapse, and sometimes this is causing sort of this sort of lagging effect of death in some of these forests, just because the trees are tipping and they're losing, there's other processes that are going on. I mean, just in general, the Arctic isn't one place. And so we have these really large differences in tree species, and some are deciduous and some are evergreen, but you also have really large differences in the type of permafrost that's there and the ice content of permafrost. So when you have many of the places in Northeast Siberia and other areas have really thick ice content in the permafrost, and this is also in Alaska. So when you have fires in these places, you're more likely to get kind of these very extreme abrupt events. And so these are just, I think it's just important to keep in mind. We talk about the boreal and we talk about the Arctic as a thing, but it is a really large place. It's pretty diverse. And so accounting for these differences in above and below ground is important in order to understand, what's happening now and also moving forward.
We have just a few minutes left, and I know, Peter, you have a hard stop and something else to get to, but I'd like to give you the opportunity to maybe get in a last word here. And you've mentioned that this is one of the areas of climate policy where you feel there's real room for progress and you feel optimism. And I wonder if you could offer any ideas. Are there ways that those on this webinar today who perhaps are not already colleagues and working in this space can get involved and be part of the policy solution here?
Well, it's a great question and an important one. I think the opportunities will become greatest when, fingers crossed, the work that is most focused on the kind of policy opportunities to reduce emissions in the boreal in North America gets published. So we have a paper that's in progress, and I don't know exactly how you all capture names of people who are interested, but the publishing a paper is just the beginning, right? What happens next is as important, and as Sue alluded to, you have to think about your audience from the very beginning of your research and kind of plan the outreach. And so we're planning the outreach, and it will involve engagement of constituencies in Alaska and in the US, in the lower 48, to bring their voices to bear in support of decision making that takes this kind of science into account. Exactly what form that takes, I think, remains to be seen, and will obviously depend on the outcome of the November election and other changes over the next several months that are impossible for any of us to predict. But I think if folks are interested in finding a way to help bring their voices forward, I'm sure colleagues at WHRC we'd be happy to work with you, I guess I would say, to help create those spaces, because this isn't going to happen just because a paper gets published. It's going to happen because people raise their voices and call on their elected officials and others to take science-based action.
Peter Frumhoff of the Union of Concerned Scientists, Brendan Rogers and Sue Natali, both scientists in the Arctic program at Woods Hole Research Center. Thank you to all three of you for a wonderful discussion today. Thank you to all close to 130 of you who joined us today for this discussion and for your fabulous questions. Please also know that much of the work at Woods Hole Research Center is supported by donations. And if what you have seen today inspired you to get involved and support this kind of work, we would also welcome you checking out our website, whrc.org, and perhaps considering making a donation. Thank you again to everyone for being part of our webinar today.